Conversations That Matter is a partner program for the Centre for Dialogue at Simon Fraser University. The production of this program is made possible thanks to the support of the following and viewers like you.
Welcome. Thank you for coming in to talk about what's become a confusing subject for me because I have no idea where the truth is, what's happening with our oceans. People tell me stuff, but I don't know where the truth is. Are our oceans really warming up?
Yeah, we have very good evidence that the oceans are warming. In fact, 2015 was the warmest year on record, and these are data that go all the way back to the early and mid 1800s.
How do you measure that, though? I mean, we're talking like water that goes in every direction and multiple depths. How do we know that?
So the recent record is a combination of satellites. So the satellites actually can measure the temperature of the surface of the ocean, and robots. So right now there's about 4,000 robots in the ocean. They profile up and down. They go down to about 2 kilometers depth, and they measure temperature all the way up to the surface. And when they get to the surface, they radio that back to shore.
What's the name of that project?
It's called the Argo Network, and it's actually an international collaboration. The US is involved, Canada, many of the major scientific ocean science countries around the world.
So these are submersibles, that just float around, or are they
Yeah,
programmed to stay in a certain position?
So they're about maybe that wide in diameter. They're maybe a meter and a half tall. And they can't position themselves. They actually float with the currents, but they can go up and down. They change their buoyancy. So it'll go up and down, and it can be programmed to go up and down on a regular basis. And when it does, it makes measurements all the way up to the surface.
So what kind of information is it gathering as it goes down and then comes back up again?
Right, so the initial ones were pretty simple. They just measured temperature and salinity. But that gives us a real good sense for how the ocean is warming over time. Some of the new instruments have pH sensors, so they're measuring ocean acidity. People are putting nutrient sensors on, oxygen sensors, so they're really starting to look not just at the physics, but the chemistry and the biology of the sea.
What I understand about climate and weather in particular is like you measure locally and it becomes part of the whole. Is that what you're doing in the oceans as well? Are you monitoring what's happening in local areas? But then how do you then knit it into the whole to get an accurate picture of what's going on? To me, it's mind-boggling.
Well, one of the really cool things about my field is that no individual scientist can do all of it, right? As you say, if you're on a ship or you're out in one spot and you have to work with colleagues, so all countries share weather data. We're also sharing ocean data. The hard part is, if you go back further in time, how do you knit together data sets that used to be ships? One of my colleagues likes to say that in the 1800s, the way they measured temperature was they threw a canvas bucket over the side, hauled it back on depth, and put a thermometer in it. Mm-hmm. And how do you, it's trying to combine that kind of data all the way up to satellites and robots. And there's some really bright people who've been working on it, and we think we've figured out how to combine data sets that way.
Yeah, as you mentioned that, I think, okay, I understand measuring CO2 in the atmosphere.
Right.
You go back to the late 1880s, you go up into the highest peaks in Hawaii and measure CO2 levels, and you can say, yep, that's the gold standard because there was not much in the way of man-made CO2 interference, and so we can measure that and go, okay, this is the basis, and we can keep coming back to that same point. But how on earth do you do it in the ocean?
So the CO2 example is a really good one because Dave Keeling, who's now passed away, started the gold standard in the late 50s. Mm-hmm. As you say, some of the measurements were at Mauna Loa in Hawaii. He also set up stations in Antarctica and at La Jolla at Scripps, where he was a scientist. Mm-hmm. Even that's tough because in addition to geographic variations, he had to worry about time variations. So did he make sure that his measurements in the late 1950s were at the same accuracy, were tied to the same standards as his measurements in 2000? For the global, we think we're getting enough data back from these floats, from ships. A lot of data has come from commercial ships. So a lot of freight companies that run across the Pacific and Atlantic are very generous and allow us to put instruments on board. So we have data that way too.
Mm-hmm. So when you say that 2015 was the hottest year on record,
right.
What was the difference between 2015 and the coldest year on record? Well, how many degrees or points of degrees are we talking?
Right. So if you go back to the early records, so in the late 1800s, where the surface temperature globally is around 0.8 degrees Celsius warmer in 2015 than it was early in the record. Now, 0.8 degrees doesn't sound like a lot, but the sort of natural background variation is maybe 20% of that.
Okay, and so as you pointed out, it doesn't sound like a lot.
It doesn't sound like a lot.
But I hear people go, oh my gosh, it is. And I want to understand, why is it a lot? Why is it something that we have to pay close attention to?
Right.
And what are the consequences if it keeps moving in this direction?
Right. So one of the ways I like to think about, climate is, people will say, well, why does it matter? Los Angeles is much warmer than Vancouver. There's life off Vancouver, there's life off Los Angeles.
Right.
But the marine organisms have adapted over very long periods of time to the climate in the region they're in. And so it's kind of like taking all the organisms that used to grow off Los Angeles and moving them up the coast. So next thing you know, they're off San Francisco. The warm water critters that used to grow off Los Angeles are now off San Francisco.
Which is traditionally quite a bit cooler.
Yeah,
yeah.
Maybe they'll be off Seattle. We're even starting to see, we're seeing migrations of animals hundreds of kilometers up the coastline with warming.
Because they're seeking out that ideal temperature for themselves.
Yeah, they just like everybody else, there's a niche that they like, and it's sort of a temperature range. And as things warm, they really don't have much of a choice. They can either move into deeper, colder water, or they can move poleward.
I've got to get you to hang on for just one quick second while we take a commercial break. We'll be right back.
Conversations That Matter is a not-for-profit program made possible thanks to the charitable support of the following and from viewers like you. Please visit conversationsthatmatter.tv and help us to continue to produce this program.
The other thing that happens is we're also changing the seasons.
Mm-hmm.
So things that might have used to happen, some important life history, whether it's a cherry blossom blooming or fish spawning that used to happen, say, in May, is now happening in April. What happens is it basically starts to pull the ecosystem apart. Mm-hmm. And people who are depending upon, a good example from where I live is there used to be a big lobster fishery south of New England. It's gotten warm enough that fishery has disappeared. So there's still lobster. There's lots of lobster in the Gulf of Maine and up the Nova Scotia coast. But the communities that used to depend upon lobster in, Connecticut, Rhode Island, Long Island Sound, they're sort of left with nothing.
I'm just thinking about the Salish Sea Marine Survival Project that's going on here, and I know that they're looking at some of those slight shifts. Are the salmon now come down to enter the Strait of Georgia or the Salish Sea, and all of a sudden the zooplankton or the phytoplankton that they would feed on aren't there because their timing has now changed.
Right. Yeah. The jargony term we use is phenology, and it basically just means seasonality. Most organisms have adapted so that if their young need prey, they're going to breed in time so that their young are there right when the prey come out. And if the prey have shifted in time, so the prey are coming too early, the salmon might breed, release their young, or other fish might breed, and the young come, and there's no food.
And that slight shift in temperature can be one of the contributing factors.
Yeah, temperature can be a big contributor to that.
Huh. So I hear about acidification. Right. And it's my understanding that acidification is primarily happening because of, for the most part, sulfur and carbon dioxide that are emitted from the burning of coal to create electrical power.
many folks might be familiar with the acid rain story from the 1970s, where, when you burn particularly high sulfur coal, you get a lot of sulfur dioxide, turns into sulfuric acid, and that's been devastating, particularly for parts of New England, parts of Scandinavia.
And you could see it in the forests there.
Oh, yeah.
Yeah.
On a global scale, that sulfur is important, particularly on land, but it's not the major player for ocean acidification. The major player is actually the carbon dioxide.
It is.
And so it's not just coal, it's also oil and natural gas, because all the hydrocarbons, when you burn them, they turn into carbon dioxide and water. The carbon dioxide's been building up in the atmosphere, so we're at levels that we haven't seen for at least the last 800,000 years. And the rate of change is about 50 times quicker than what we've seen in the geologic past.
Even though we've had periods of higher CO2 concentrations.
Right. You can go back, many millions of years ago, and carbon dioxide was elevated, but it was a gradual shift over time.
Allowing all those other systems to adjust.
But we're hitting it with a big shock. We're basically taking all this carbon, dumping it into the atmosphere really quickly. And right now we release about 10 billion tons of carbon, most of it from fossil fuels. About half stays in the atmosphere, about half is being sucked back into vegetation and soils. Or sorry, half into the atmosphere, a quarter back into soils, and another quarter is going into the ocean.
This will be our second break. We'll be back in a moment.
Conversations That Matter is a not-for-profit program made possible thanks to the charitable support of the following and from viewers like you. Please visit conversationsthatmatter.tv and help us to continue to produce this program.
I had Tim Flannery, the climate commissioner from Australia, back in the government back in the earlier part of this century. And one of the things that he was talking about was the cultivation of kelp and seaweed beds to consume carbon in the oceans. Is that a practical solution?
So, that's not the only solution that's been proposed. People say, well, we could dump limestone in the ocean, because what happens when the carbon dioxide gets in the water is it actually reacts with water to form carbonic acid.
With limestone?
Well, just in the seawater, it reacts to form carbonic acid. And one way of neutralizing that would be to grind up limestone and dump it in the ocean. The problem is, going back to that number I mentioned before, 10 billion tons of carbon a year. So think about all the coal trains, all the oil pipelines, all the natural gas pipelines. A quarter of that carbon is ending up in the ocean. So any attempt to grow kelp or algae, what are you going to do with that kelp? You can't let it rot. You'd have to harvest it and store it someplace. So I think the best solution is to try to limit the emissions in the first place. So rather than dealing with the pollution once it's in the atmosphere and the ocean, try to shut it down at the source.
So if warming just ever so slightly affects timing, what was the word that you used?
Phenology.
The phenology.
So there's your word for the day.
Yeah, there's my word for the day, phenology. What does acidification do? And what does it do if it goes unchecked?
Right. So one of the reasons we're concerned is there's lots of plants and animals and microbes in the ocean that build shells out of calcium carbonate. So if you've ever seen a picture of the White Cliffs of Dover, that white, chalky white is actually microscopic shells of planktonic organisms that were settled down to the bottom of the sea a long time ago and built up. When you make the water more acidic, it's harder for those organisms, those plants and animals, to build their shells. So it's everything from small little plankton all the way up to coral reefs. So corals build their shells out of that. One of the things we've worked on is shellfish. So scallops, mussels, oysters, even some of the crabs and lobster have calcium carbonate in their shell.
Okay. Are you scared when you're looking at what's happening right now?
So right now, I'm probably based on the evidence, probably more frightened about climate change because a warming ocean affects almost everything. You know, there was some news out of Australia recently. With the recent warming, we saw a very large El Nino in the Pacific.
Yes.
So all of the tropics warmed. And the Great Barrier Reef, the corals, are very sensitive to extreme temperature. And they underwent something called coral bleaching. So corals are little animals. They're little polyps that look like sea anemones.
Yeah.
And they have microscopic algae that grow inside of them. And that's what gives the color to the corals. When the corals get stressed, they expel the algae, they bleach, they turn white. And if they're under so much stress that they're sensitive to diseases, and also can lead to a lot of death of corals. And the Australian scientists found that about a third of the Great Barrier Reef that they studied, the corals had died.
Our final break, and then we can get to the exciting conclusion of this conversation. We'll be back in a sec.
Conversations That Matter is a not-for-profit program made possible thanks to the charitable support of the following and from viewers like you. Please visit conversationsthatmatter.tv and help us to continue to produce this program.
So is this different than the El Nino of the late 1990s?
So we've had, I can't remember now if there was the 82, 83, there was the 97, 98 were the really big El Ninos. We've had coral bleaching and death in all of those, but this was the first one to really hit the Great Barrier Reef. Much of the Great Barrier Reef is protected, and people thought that perhaps it would be less sensitive to these climate effects because there's less pollution, there's less human disturbance, but it didn't look like that held true for this
Well, I understand
warming.
that there's a fairly massive El Nino that's happening right at the moment. What
Right.
does that do? Does it offset that, or
Yeah,
is that wishful thinking?
We still have these warm and cold cycles in the Pacific. The problem is the background temperature is gradually warming with time. So the El Ninos appear stronger because they're on this background warming temperatures. The La Ninas will help. These cold events will help the corals, but we don't know how quickly it'll take. Having a mortality rate of 1/3 is enormous. And we don't know how quickly those reefs will be able to recover.
What does a warming ocean temperature do to the ocean's ability to act as a carbon sink? Because people will point to that, and many people will say, well, the reason that we're having a global warming pause is because the ocean is absorbing that additional heat.
Right. So there's two parts that the ocean plays, both very important. One is that the ocean slows the rate of global warming. That has two sides, right? You can think of the ocean as a giant flywheel, and it takes a long time to heat up water. I take my coffee cup. Everybody knows how trying to watch a pot boil. It takes forever. The problem, and I like to sometimes joke that instead of global warming, we should call it ocean warming, because most of the additional heat, it's not in the atmosphere. It's either in the ocean, or it's been used to melt ice. So melt
Which is
glaciers
fresh
and
water, isn't
which
it?
is fresh water. The couple of problems. One is the ocean's absorbing a lot of heat. It actually expands. So a warming ocean is also leading to sea level rise. When you melt ice on land, the glaciers, ice sheets, you're also adding more water to the ocean. That causes the ocean to rise. And then you're building up this big pool of heat in the ocean that will eventually get back out. So this climate pause, and there's a lot of arguments and about exactly how to interpret the data. 2015 sort of put that to rest. It was by far the warmest year on record, both on land and in the atmosphere. So we look to be continuing on this long-term decadal trend of warming.
So I've had people say to me, yeah, but if you take a look at what's happened since the last ice age, 17 some odd thousand years ago when it sort of officially ended, 35,000 years since it peaked, well, the ice has been melting, ocean levels have been rising.
Right.
We know this. So what's different?
So, things have changed a lot from the last glacial, but things the climate actually stabilized. So the last 10,000 years, the geological term, it was the Holocene. But you can also think of it, it was the birth of civilization. It was a stable climate where you could set up agriculture reliably. You had ice-free areas, you had relatively stable sea levels, stable climate. It's really been the period where humans have flourished. We're now, the rate of change of carbon dioxide, carbon dioxide did change from the glacial period, the cold period, carbon dioxide was low. This warm, what we call Holocene or interglacial, it was relatively high. We're now up here. And we got there about 50 times faster than the transition from the glacial to the interglacial. So we're moving into a world that's very different than anything we've seen in the past. And I think there's some risk involved in here that we don't actually know where we're headed.
Well, despite the IPCC reports and the conference in Paris and so on, I don't really see anything happening that's going to slow it down. Even though people are saying it, that they want to do that. And does that not cause you concern?
It does, and I was joking with people earlier today. After I went to the Copenhagen UN Climate Conference, and that was
in 08, wasn't it?
Yeah, that was in 08.
Yeah.
There was a lot of excitement and build-up before that conference, and a bit of a letdown at the end. I think actually we've started to make progress, and the Paris Accords I think are a good first start. The other thing is some of the major players, there's lots of reasons that on their own they might change their behavior. So in the United States, for example, emissions have been declining with time, switching away from coal to natural gas, not as much because of regulations, but because of economics.
Natural gas will be the real driver, won't it?
Yeah, natural gas has been cheaper. In China, they are installing solar energy, wind energy at an amazing rate, faster than most of the rest of the world put together. And in fact, Chinese emissions dropped last year, and it actually made the global emissions rate slow down or even decline. And for China, it's not just a matter of climate change, though they're very concerned. One of the biggest drivers is air pollution. You just can't, burning coal has a lot of downsides. It has, it's driven the Industrial Revolution, it has a lot of positives, but unless you're very careful, it leads to a lot of air pollution problems. So, I think there's a glimmer of hope that, air quality, economics might actually lead to improvements. And then when you combine that with more awareness and political discussions, maybe there's hope for the future.
Well, and add in diligent, consistent, and credible scientific work such as you're doing. Thank you for doing that.
Oh,
Thank you for coming in and joining me.
Thanks.
Appreciate it.